This video is going to be about moles, and by the end of it I'd like you to know what a mole is in chemistry, and I'd also like you to know why it is important. Okay, so what is a mole? Quite simply, a mole is a word that represents a very particular number. Let me give you some other examples of words that represent particular numbers. A pair, for example. Well, the word pair represents the number 2, as does the word couple. If I were to use the word trio, we might know that that is a word that represents the number 3. Or if we were to use the word dozen, we would know that that is a word that represents the number 12. Well, in just the same way, the word mole represents a very particular number, and that number is 6 times 10 to the power 23. So that is a 6 with 23 zeros after it. So the word mole represents a very particular and very, very big number. Incidentally, you might be interested to know who came up with this very particular and massive number. Well, here he is, Avogadro. And in fact, the number is also often referred to as Avogadro's constant. So, we know that the word mole represents a very particular, a very big number, 6 times 10 to the 23. But this doesn't tell us why it is so important in chemistry. So let's have a look at the definition of the number 6 times 10 to the 23. It is the number of atoms in 12 grams of carbon. The number of atoms in 12 grams of carbon. So it shouldn't really be a surprise that it is such a massive number, should it? Because atoms are unbelievably tiny. So in 12 grams of carbon, there are 6 times 10 to the 23 atoms. So can you see the relevance of the number 12? If you can't, it's probably time to have a quick look at a periodic table. And here one is. I would like to draw your attention to carbon, and in particular to the relative atomic mass of carbon, which is 12. This means that relative to a hydrogen atom, it is 12 times more massive. Now do you see the importance of a mole and the relevance of the number 12? Look, let's get rid of some of these bits and the periodic table. So what we're saying is the relative atomic mass, AR, of carbon is 12. And in the last slide, we learnt that 1 mole of carbon atoms has a mass of 12 grams. A relative atomic mass of 12 and 1 mole, 6 times 10 to the 23 carbon atoms, has a mass of 12 grams. So what we're saying is, if you have 1 mole of atom, 6 times 10 to the 23 atoms, of any element in the periodic table, the mass of that element will be its relative atomic mass in grams. An example: hydrogen. Hydrogen has a relative atomic mass of 1. So if you had 1 mole of hydrogen atoms, the mass of hydrogen you would have, or the mass of hydrogen atoms you would have, would be 1 gram. See? Lithium. Lithium has a relative atomic mass of 7. So guess what? If you had 1 mole 6 times 10 to the 23 of lithium atoms, what would be the mass of lithium that you'd be holding? Yep, 7 grams. It's relative atomic mass in grams. And it gets even better. We can do this with molecules as well. Take, for example, a molecule of H2O, water. First, let's work out the relative molecular mass. Well, there are 2 hydrogen atoms in water, and we know the relative atomic mass of each hydrogen atom is 1. It's 2 of them, so we'll multiply it by 2. And then we need to add that to the relative atomic mass of oxygen, which is 16. We put those together, we end up with a relative molecular mass of 18 for water. So, just imagine you had 1 mole of water molecules, 6 times 10 to the 23 water molecules. What would the mass of that volume of water be? Exactly 18 grams. Or carbon dioxide. We've got carbon dioxide over here. We've got 1 carbon atom with a relative atomic mass of 12. We've got 2 oxygen atoms with a relative atomic mass of 16 each. We add all that up, we can find the relative molecular mass of carbon dioxide is 44. So what would the mass of 1 mole of carbon dioxide molecules be? Exactly 44 grams. It's brilliant. Okay, so we now know that a mole is a word that represents a number, the number 6 times 10 to the 23, so a really particular and really big number. We also know that if you have 6 times 10 to the 23 of any atom or molecule, then the mass that you will have is the relative atomic or relative molecular mass of that particular particle in grams. But why is it useful? Well, a colleague of mine explains it like this. Imagine if you had £50 in 5p pieces. You put all those 5p pieces into a bag and you took it to the bank and you wanted to pay it in. Well, there's no way that they're going to spend the time counting out every single one of those 5p pieces. Instead, they take the bag and they check its mass. Because they know what the mass of, say, £1 worth of 5p pieces is. And so they can use the mass of that many coins to work out if they've got the right number. It's exactly the same in chemistry. Often chemists will want to know how much they have got of a particular substance, or they want to know how much of a particular substance they have made, or they want to make a particular amount of a substance and they need to know the correct masses of the reactants that they should put in. And there's nobody that is going to be able to, or can be bothered to, count out each and every atom or molecule. So instead, we check the mass of the substances. And then using the idea of moles, we can work out how many atoms or molecules we have got. Moles.